what I'm talking about in the last lecture. Okay, because as I said before the last lecture, we will enter into some modern electromagnetics and optics. It is different from the classical Maxwell equation. So some content I think are not easy to understand, also difficult. So this chapter I think is for students. I think you should learn some basic knowledge. You are not necessary to understand this deeply. I think it's need time. Okay. So I think this content in this chapter is important for some researcher. So in last lecture we talked about the spontaneous emission and black body radiation. So I like to talk about the black body radiation first. Okay. I go to black body. So black body. So for black body, consider black body. So what's a black body? Black body, it has a very important feature. Is we call it at a thermal equilibrium, the emission. Okay, the black body has temperature. Okay, at some specific temperature, they emit electromagnetic wave. Okay, and this emit electromagnetic wave will balance with the electromagnetic wave from the outside. Okay, that means the blue line and the black line are balanced each other. Okay, at a thermal equilibrium. So mathematically, is a black body? Is called emission coefficient equal to the absorption coefficient equal to 1. Okay, this is absorption coefficient. This is emission coefficient. Okay. Means emission coefficient will equal to absorption coefficient. Okay. Consider a black body. Okay. They absorb electromagnetic wave, then the temperature will increase, or maybe they give some temperature, then they emit some electromagnetic wave, go to outside space. The incoming wave are balanced outcoming wave. Okay, so thermal equilibrium can be achieved. This is called a black body. The emission equal to absorption equal to emission coefficient equal to absorption coefficient equal to 1. Because everyone knows the absorption coefficient equal to 1 minus R. Then we go to R go to 0. So reflection coefficient equal to 0 for black body. Okay. This is black body. Another body is called a white body. White body, the R equal to 1. Okay, that means they totally reflect electromagnetic wave. So no absorption and no emission. So absorption and emission equal to 0. They call white body. This is a basic concept. Okay, so important keyword is thermal equilibrium. Okay, at thermal equilibrium, the two processes, the emission process and absorption process, are balanced with each other. So this is the first important concept for black body. Another is for the black body radiation spectrum. So the intensity, the emission intensity per unit volume. Okay, per unit volume, per unit frequency. Good. Per unit volume, per unit frequency. The intensity of the black body radiation law, something like this. Okay, here it's around 500 nanometer. The temperature is around 5,800 K. Okay, so it's sunlight. So sunlight, the emission spectrum with a peak at the visible light regime. Okay, this is similar to sunlight. So sunlight can be, say, a black body with temperature 5,800 K. Okay. So at room temperature, something like this, very far from. Okay, here is 10 micron. 10 micron. It's around 300 K. K here is Kelvin temperature. So for black body radiation, they said the emission spectrum only depend on the temperature. They only depend on temperature. Okay. And this peak value are quite different. Okay. This is the reason why we see the visible light from the sun. The sun's temperature is higher, but we cannot see the infrared. Okay, because our body they emit infrared. Because our body is around here, around the room temperature. When we emit the peak, it's about 10 microns, so we cannot see the infrared. Okay, so this is black body radiation. So in last lecture, I talked about how to calculate. Okay, how to get this curve. Okay, what's the basic procedure to get this black body? To get the black body radiation spectrum. Okay. What's the basic procedure? Okay. How to get? So they have two steps. One is number of mole. Okay. The number of radiative mole. Here, every mole are radiative. Okay. Per unit volume, per unit frequency. So here, how to understand this? I think it's easy to understand use a case base. Maybe in last lecture, Xingang told me use a case base is better. I think his suggestion is good. So I like talk about this use a case base. Okay, consider case base. It has a sphere. Okay. Then it has a shell. Sphere, okay. It has a shell. I already know the total volume for this shell of sphere shell is 4 pi k squared dk over 8. Here I only consider kx larger than 0, ky larger tthan 0, and kz larger than 0. So this is a quarter hemisphere. Okay, just one of the 8. Okay, 4 pi k squared over dk. Okay, this is just a spherical coordinate. Okay, so this is the total volume for this shell. Okay, I mean I give a very small change with this k. How many mole? How many mole will exist within the shell region? How many mole? So I just over a molar volume. Okay, I already know that for given a volume, given a small box, a cavity with a dimension maybe ABD. Okay, it's not problem. It's ABD. Okay, I already know the minimum resonance wavelength A should be half wavelength. Okay, it's a minimum resonance frequency of similar. Okay, so here I just derive the lambda equal to 2a. It's not good. I derive above here. It's better. So a equals to half wavelength. So lambda equal to 2a. Then I go to the k here is 2 pi over lambda equal to this 2 pi over 2a equal to pi a. Okay, so this means in the spatial domain, this 1D problem, x, this is the minimum resonance frequency. Here is a half wavelength. Okay, is spatial domain. But in the K domain, okay, the minimum distance here is just a pi over A. Okay, so here, this is the total volume I over pi over A, pi over B, and pi over C. Okay, this is so for a small cubic, this is a spatial domain. I do the Fourier transform. Do the Fourier transform. Go to a K domain. Okay, this is a KA is similar to KB and a KD. Okay. So delta K, I mean, is KA multiply KB multiply KC is pi over A, pi over B, and pi over, we call D. ABD. Okay, KD is a pi square volume. It's pi square volume. So here is pi square or volume over volume. Okay, so in the denominator is a minimum mode volume in K space. Okay, it's a minimum volume in K space. Okay, I mean, okay, here is a total volume for this shell. Okay, I over this is just number of mole. Just its number of mole can contain in the shell region. Okay, this is a total volume. This is a minimum small mode volume. Okay, it's just the Ka. Okay, you can see here, this is a spatial domain, this is a K domain. Okay, this is spatial. This is spatial. This is a K domain. Okay. I use change color. This is K domain. Okay, this is just K just equal to 2 pi over lambda equal to pi over 8. Okay, so it's pi over 3 over V. I just go down further. So it's easy to derive, okay? Then I multiply 2 here because they have 2 polarization, okay? There has a 2 polarization, TE and TM similar to that, okay? So I finish. This is just the number of relative mode per unit volume per frequency, okay? Then I simplify this equation, see what happens. So here, I just simplify this equation. This is 4 pi k squared dk over pi 3 v. Now here, I equal to 8. 8. Oh, this is also 2. Okay, here. Okay, so I just is pi squared k squared dk. Okay, this is with the K domain. Okay, I can convert K domain to frequency. Okay, everyone know F equal to C. Oh, sorry, I use V better. V is a frequency equal to C over lambda, right? Equal to 2 pi C over F, right? 2 pi C over F. So lambda equals to C over 2 pi, no, 2 pi C over K. Okay. So here V is the frequency. Okay, lambda equal to 2 pi over K. Lambda equal to 2 pi over K, so alright. It's C over 2 pi over K. So it's Ck over 2 pi. So K here equal to 2 pi V over C. Okay. So this is equation. Okay. Then I substitute to see what happened. K squared is 2 pi V over C squared over pi squared, and dk dV 2 pi over c. So finally, it's 8 pi square, v square, and c square. 2 pi, sorry. Okay. dv. This is I get. Okay. I just do this very simple transformation. So I just see the lecture note, what happened. So I go to the photonic. It's a lecture note. Oh. Spontaneous emission and light emitting. Okay. So I get this. You can see a pi v square over c square. Same. So here I just use k space first. Then I do some transformation with dv. Okay. Do some very simple transformation. You can see here. I use k space get the k square pi square dk. Then I connect k with 2 pi v over c. Then I do this. Get same result. This is the local density of state. Okay, this is local density of state. Local density of state. It means the number of allowed mode in this per unit frequency. Okay, I go to this picture. It's better. Okay, this is a shell. It has some shell. Okay, it has some shell in here. Okay, this is the number allowed mode per unit frequency per unit volume. Okay, this is called LDUS. This is the first thing we must do. Okay, there are two steps. Okay, one is number of mode. Okay, another just mean energy per mode. Okay, how to get the mean energy or exploitation value of energy for each mode? Okay, the first step we know the number of mode per unit frequency per unit volume. Then we know the mean energy per unit mode. We multiply them together, we can get a black body. Okay, so mean energy is very simple. Okay, it's not difficult. They said, oh, for each mode, we can have 0 photon with E0 equal to 0. Okay, if we have 1 photon in this mode, the E1 equal to h bar omega. H bar is just a reducible Planck constant. Okay. If we have 2 photons, the E2 has 2 h bar omega. Oh, these are many different cases. Okay. We don't know how many photons in each mode. Okay, because I said for electron, one electron occupies state, another electron should occupy different state. We call the Pauli exclusion principle. That means the 2 electrons cannot occupy the same state. Okay, but a photon is different. Photon, any number of photons can occupy any allowed state. Okay, so in each state we can have 0 photon, 1 photon, 2 photon. We don't know. Okay, but we know that the probability for energy is proportional to the exponential this energy over kBT. This we call this Maxwell. It's a Boltzmann distribution. Okay, Maxwell-Boltzmann distribution. Okay, we don't know how many photons in each mode, but we know if this photon number is higher, it has a smaller probability, right? It means if a photon number is smaller, it has higher ability. If photon number is very high, it has little ability. Okay, we know that. Okay. So how to get the average energy? It's very simple, just statistics. Okay, just n h bar omega n go to 0 infinity. Okay, this is energy for n photon. Multiply some is a probability. Okay, but this probability may not be how to say. This probability is not normalized, so I normalize. I normalize. Okay. This is the photon number. This is the probability I normalize. Okay. So finally, H bar. So finally, I get this very famous equation: H bar omega over E H bar omega kBt minus 1. Okay, minus 1. This is a mean integer. This is a mean integer. Okay, this is the mean integer per mole. Okay, this is mean integer per mole. H bar omega E H bar omega kBt minus 1. If omega is very small, omega is small, I mean it's low frequency, right? If omega is small, here I can use the Taylor function. So finally, H bar omega equal to H bar omega kBt. If 1 plus minus 1 equal to what? kBt. Okay. So at a low frequency, it's equal to kBt. Everyone knows the kBt. kBt is just a kinetic energy for this ideal gas. Okay. But this equation is for all the frequency, no matter lower or higher. Okay, this is quantum mechanics. So finally, we finish this row. They call it radiation energy per unit frequency per unit volume. Okay, this is finally we get this black body radiation law is just the LDOS, just number of mole that over this average energy. And finally we get this A pi h v square c square 1 over E h v kBt minus 1. We get this equation. HV square. Okay, HV here equal to H bar omega. V is the frequency. V is frequency. V, I use this V just 2 pi V just equal to omega. Okay. So we get this. This is the black body radiation energy per unit frequency per unit volume. So it's not difficult. It's very basic. I think it's not difficult for this part. If you understand, it's just 2 steps. Okay, this left LDOS, that is the energy. Why is very important? Because Einstein used this to get this spontaneous coefficient. It has 3 situations. One is spontaneous emission. Okay, spontaneous emission is from the excited state to ground state. Another, if it has incoming photon, then we have 2 photons come out, and these 2 photons have same frequency, polarization, direction. Okay, it's a coherent. They call it stimulated emission. Stimulate is spontaneous. Okay, another 3rd step is just absorption. Okay, from the ground state to excited state. They call it absorption. Absorb the photon energy. Okay, they have the 3 different. I use mistake. 3 different procedure. 3 different procedure for the electronic transition. Okay. So spontaneous emission here is no incident photon. Okay. Just atom from the excited state to ground state emit 1 photon. Okay. That stimulate emission, they have incoming photon, then interact with electron, then they have 2 photons. They have coherence, they have incoherence. Okay. This is stimulation. Stimulated emission is for this laser. stimulate. Let me see this. Stimulating. Okay, stimulating emission. And it's absorption. Okay. So I think the most important thing is a detailed balance. Okay. I means the net, the dn1 over dt net should equal to 0. That means at thermal equilibrium. Okay, this is important. At thermal equilibrium, at thermal equilibrium, the number of the density, the atom density at the ground state, the net change of number of states at ground, the number of atoms at ground state equal to 0. This is called detailed balance. That means the atom cannot be increased or cannot be decreased. Okay, at the ground state if a thermal equilibrium. Okay, so I can split the dn1 over dt with 3 parts. A dn1 over dt spontaneous emission, right? The dn1 over dt stimulated emission, and plus dn1 over dt absorption. I just split 3 parts. 3 parts should be balanced, okay? Because it's thermal equilibrium, okay? So no net increase or decrease. So the 3 parts. How about the first part? Spontaneous emission. For spontaneous emission, just add a coefficient from 2 to 1 and n2, right? Right. This the n1 equal to, because from here down here it increase the number of atom at the ground level. Okay, so a to 1 equal to n2. This is spontaneous emission. For stimulated emission, this is b to 1. It adds a b coefficient, n2, and rho. This is important. Rho is a black body antigen. Okay, antigen, black body is antigen spectrum. Okay, black body antigen spectrum. Okay. Here, and absorption just decrease. B1, 2, N1, and 0. It has 3 terms. It should be balanced each other. Okay, you can see here the spontaneous emission no rho because of no incident wave. It's no incident wave. Okay, for spontaneous emission. But stimulated absorption has incident wave, interact incident wave with electrons, so it has rho here. Okay, the minus for absorption because absorption will decrease the number of atoms at the ground level. Okay. So this is very easy to understand. These 3 steps, it should be equal to 0. Balance, okay? So Einstein found that, why Einstein is very smart, what's his very important contribution? They found the N2 equal to N1 equal to, his contribution is N2 equal to N1 equal to maybe gap, we call gap, maybe KBT. H bar omega is better. It's photon H bar omega. Okay. This is his finding. It's also a Maxwell Boltzmann statistic. Okay. They found, okay, initially, people don't know spontaneous emission exists. They don't know. They assume they have not exist. But they found, Einstein found the N1 and N2. They found the N1 and N2 are not balanced each other. It means the number of the atom at excited state and number of atoms at ground state are not well balanced at thermal equilibrium. They satisfy these statistics. Okay, this is a statistic. It means number of atoms at the excited state has smaller. Okay, because it's Maxwell-Boltzmann statistics. Okay, they use these statistics to balance this. So I just draw N21. Here I don't consider degeneracy. I use simpler. EHV over KBT. Okay, here. And plus B21 EHV over KBT. Okay. And multiply the black body radiation law. It's just EHV. Sorry, not H bar B. Just HV over KBT minus 1 as FV is some constant. So FV here, so I just draw this. I don't use FV, I use 8 pi HV3 C3. This black body radiation law. This should be balanced B21 8 HV3 C3 EHV KBT minus 1. Okay. This is just detail balance. Okay. It's detail balance. That means the net or the number of atoms at ground level should be balance each other. Okay. No increase or no decrease. So I just use this Boltzmann statistic to substitute them. So finally, I do some algebra. Einstein found the A21 equal to 8 HV3 C3 equal to B21 and B12 equal to B21. This is his finding. Okay, this is his finding. If I absorb the Einstein P coefficient for absorption and stimulation are same, and the spontaneous emission has some coefficient. Okay. You just multiply this and then compare the coefficient. Okay, because T is arbitrary, you can get this. Okay. So I think the most important part is here. Okay. Because initially if you know this term, if N1 equal to N2, they get this identity if N1 equal to N2. Okay. But here N1 and N2 are not balanced because Maxwell-Boltzmann statistics. I mean, at the excited state, the density of atom is smaller than the ground state. Okay, it's a Boltzmann statistics. So this is the reason they found this. Okay, but at that time people said Einstein will get this Nobel Prize due to this contribution. But Nobel Prize cannot give this contribution, but other contribution like a photoelectric effect or something. Okay. This is a very important thing. He contributed for its spontaneous emission. Okay. We use the black body radiation law. Okay. I give this relationship and this relationship. It's done by him. Okay. So this is something I want to repeat. So today I will talk about this classical picture and semi-classical picture for spontaneous emission. Classical picture. What's the classical picture for this spontaneous emission? Consider it has dipole. It has earthing dipole. Okay, it has dipole. Earthing dipole source. Okay, this dipole source will produce electromagnetic wave. Will emit electromagnetic wave. Emit electromagnetic wave. This dipole source in free space. But if I put a sphere, maybe dielectric sphere around this dipole. So what happens? If I put a dielectric sphere around this dipole, okay, they will excite some mode, right? For dielectric sphere, we excite this current, something like this. Okay, the current direction should be aligned with the dipole. So M here is magnetic dipole. This is a magnetic dipole, and this excites some field. Okay, it excites some polarization current within this dielectric sphere. Okay, and will interact with dipole. This scatter field will interact with dipole. This scatter field. This is immediate field from this dipole. Okay. And change the field around this dipole. A change field. Okay. This is physical picture. Okay. So according to pointing theorem, okay, you learn the pointing theorem. If I use a closed surface to enclose the dipole source and is some object, my dipole sphere. Okay, this we call S because N is S. We know that the energy, okay, M into this surface, the real power and into the surface will dissipate, right, by the sphere. Here, we know sphere is lossless, so does not dissipate any energy. It does not dissipate any real power. But here we have source. We have a source term here. Okay, that means this source term will provide some real power. Okay, it has to provide some real power. It's J E here. Okay, dB. So I change the sign. Maybe it's better. It's 1, 2. So I change the sign. Dash ds. Okay. Equal to 102 minus V real part and J dot E dV. It's better. Okay. So here, this is better. They said, okay, the real relative power, okay, this is the virtual surface. The total, okay, relative power emit out from this closed surface and provide by the source. Okay, provide by the source. So it's provide by the source. Provide by the source. So total power emit out from this closed surface. They provide by this current source. You derive this equation. Remember, but your derivation does not contain a source. You just assume they have some lossy material. The J equal to sigma E, right? So there's a sigma E squared similar to that. Okay, it means it has absorbed power by this absorbing material. Here, no absorption material because its dielectric layer is lossless. This is lossless. This is lossless. But it has source. J has source. Okay. This is a current source. It has dipole. Okay. When the dipole emits electromagnetic wave, they provide this relative power. So this relative power is just okay. The relative power over this dipole, okay, is just provided by this source. So this is first equation. See what happened. This is very interesting. So the J, everyone know the J equal to the partial P or partial T. The P is the polarization, right? It's for this dipole. It's just I omega. I use I omega. Okay, mu delta R plus R0. Okay, R0 just location of this dipole. It's R0. It's location of this dipole. The J equal to I omega mu. Okay, so delta. So E, how about the E? You learn the E. Okay, The E just omega. You learn this is a free space. If in free space, it's J. Sorry, not J. It's I. Omega mu didegree function R prime J R prime dr prime. Okay. So here I just use this. So I just change this omega square mu square. No, it's not mu. It's I call this a little bit confused. Another notation, so better. Called what? It's called P. Better. Okay. So it's omega square mu P, the didegree function R0. Okay, this is something we get. Because this delta is delta source. Okay, it's delta source. But here, remember here, it's not in free space. It's not in free space here. It's not in free space. Because I put the dielectric sphere is very near from this dipole. Okay, I mean dielectric sphere will affect the field at this point. Okay, you can see here this equation. If I use free space green function, if I see this didegree function in free space, finally I get this G. Sorry, it's R. The source and it's R0. Let me clarify. Because I said J is a delta function, so I get this equation. Okay. The E field is just R0, also R0. Also not R0. It's R. The ER. Then I pull them together. dW dt equal to dW dt just this is dW dt, just called a dissipative power. Okay, this dissipative power is just converted to radiative power. So dW dt is 2 omega in main part, and mu equal to, now mu is P, not confusing, P star with E R0. P star is R0. So finally, we just get this 2 omega 3 mu and n imaginary part green function R0 omega. Then omega 3 mu P. Something like this. Let me explain this. Okay, this is some derivation. You can see here, the green function, typically I use a free space, I get this. First we consider free space. If we know that J is just some delta function, okay, the P is polarization strength, okay, I just substitute to this equation, I get the E field at some observation point is omega mu P equal to G. G is just free space green function. Here, because we know, according to this equation, you can see this equation. I said this is radiative power, okay, in a closed surface, okay, including the source and the sphere, okay. This is radiative power, okay. According to a Poynting theorem, this is equal to this dissipative power by the source, okay. The J is the source and dot E. Here the J, because it's delta source, this source point, this source only has one point, right? Because it's delta source. So J is some delta function. So E, so only the field at this point contributes to this integral. Okay, because J is delta function. Delta R plus minus R0 and something like this. So only E field at R0 contributes to this integral. Okay. So I just go through this. And means from this equation, you can see here, this is a relative power or dissipative power. Okay. This is a source, this is a field. Okay. Okay. This is a volume integral. But J is very special. J is a delta function. Okay. At R equal to R0. So only E field at R equal to R0 contributes to the integral, right? So finally, and this E field also can be represented by the Dirichlet function. So finally, you can see here, and this is some constant that don't care about this. Finally, you'll see that this is imaginary part of Green function. Why they have imaginary part? You can see here. This is I omega mu in here. Okay, this is real. This is real part. This is I omega mu. This is a Green function. So I go to the imaginary part in here. Okay, because this is I omega mu. So I change to real part to imaginary part. I move the I omega. I move the I here. Okay, so I change to the imaginary part. You can see here, they only depend on Dirichlet function from the source point and the field point at the same point. Okay. Okay, source and the field at the same point due to integral. Okay. Okay, so this is let me give an example. What's the meaning of that? It's a little bit confusing. But this is the important concept. Okay. So consider it has a PEC plate. Okay. This has dipole. I give you assignment to you. This is R equal to R0. If this is a lambda of 4, okay. If this is lambda of 4, the wave will go from here, reflect back, go here, right? So they are in phase. So it's a lambda of 4 multiplied 2. This and this boundary, they produce another. This is k. Okay. This is another pi by the boundary, by the PEC. Okay. So here is 2 pi lambda, lambda 2, so pi. Okay. So here is 2 pi. Okay, 2 pi. So it's in phase. So you can enhance the emission. So the field point at here, initially, free space, if this is the dipole, okay, this is free space. The dipole also produces a field. This is source, also produces field at the same point, okay. It means Green function. Green function, R0 means they have a source at R0 and produce the field also at R0. Okay, this is the imaginary Green function. Okay. This is source point, the field point. But the field point and the source point are overlap. Okay, are overlap. Why they have this just due to this integral? Due to this integral. Because J has delta function. The E only has some delta function at this location has contribution. Okay. And the E also connects to Green function. So this is a reason. Okay. This is a reason. Okay. So this is we call this is similar to this imaginary part Green function R0. We call it free space. It's a free space. Okay. But why I put a PEC, if I design it properly, this field will enhance. Right? Because it has two kinds of field. One is from the free space Green function. Another just from some reflection. Right? You have reflection because the wave from here and reflect back and go here, similar to that. Right? If a wave from they will emit a wave that goes to PEC and reflect it back to here. So add them together. So they change the Green function. This Green function is not free space Green function, but inhomogeneous Green function. Okay. Okay. The inhomogeneous Green function. let me explain this again. Okay, if without the sphere, the E field at this dipole location is just incident field from this dipole source. Just incident field from this dipole source. Okay? But if I put the sphere along here, the E field at this dipole location has two parts. One part is incident field from the dipole source, another is scatter field from this sphere. Because the incident field, excite is scatter, is resonance, they will emit, they have some scatter wave to do here, to change the field at this dipole position. Okay. So this E field is just total field, including the incident field by the dipole and the scatter field from the environment. So that you can change the field at this location. This is very important. If you change the location, you can change the emission power. This is the reason for Yagi-Uda antenna. Okay. This is dipole. Okay, free space. They emit everywhere, and the emission power is low. I put a PEC because this field at this point change, right? Because it's reflected back, go here. They change the field at this point. So this equation, just here, you can see, just here. This is very important because J is delta function. So only has E field at this point as contribution. So this is the reason why the green function, the source point and the field point are overlap. Okay, source point and field point overlap. Also they have imaginary part. Because they have I omega here, so this is the imaginary part. Okay. So this is the imaginary part of green function. It's a physical meaning. Okay. So imaginary part of the dielectric green function in the inhomogeneous space, they determine the dissipative power or relative power. This is very important. If you change the electromagnetic environment, you can put some scatter, right, to enhance the E field at this dipole position, enhance the imaginary part of the green function. Now you can enhance the relative power. Okay, they can enhance the relative power. Okay, just similar to this Yagi-Uda antenna. Okay, initially only had incident field. Okay, free space. And I go here, reflect it back. Okay, the in phase, add them together, so it can enhance. Okay. So this is a very hard to understand because you can see this is far field. This is far field relative power. I mean the total relative power. I go to enclose a very large sphere, a total relative power. Okay, is equal to this. Okay. But they depend on what? Depend on this point. Just one point. Dielectric green function. Okay. It's very magic. You just control this point, one point, the dielectric green function here. You just control all the relative power. Okay. This is the imaginary part of green function. So this is very important. The green function is inhomogeneous. I go to the next slide. Then we can have a break. So, if there has a lossy material, I put some metallic nanosphere, there has a dipole, then the metallic sphere has plasmonic effect, they have plasmonic resonance, they also can enhance. They also can enhance the field here. But the field has two contributions. One is called relative part, another called non-relative part. Okay, I just draw this pointing. Okay, it means, okay, this source this is provided by the source. Okay, it has two parts. One is just for the E cross H real part ds. Okay, this is called relative. Another, just sigma E squared dV. Okay, this is called non-relative. Non-relative. This is mathematics. Okay, so what's the physical picture? So when I put the metallic nanosphere, okay, the dielectric green function, the imaginary part of the dielectric green function at this point change. Okay, because they have two parts. One is incident wave from dipole itself, another is scatter field from this sphere. Okay, because the sphere, one sphere resonance, when they are close to each other, they have a very strong plasmonic resonance. They can enhance the field at this dipole point. Okay, so this is a total power. The total power has two parts. Okay, they emit the total power. One power was absorbed by the sphere because the sphere has loss. Another they are related to far field. Okay. So total radiative power split into two parts. One is a radiative part, I mean it's related to far field. Another is a non-radiative part, just absorbed by the sphere. Okay. And then the two parts, the ratio radiative part over non-radiative part just by this. You can verify it very easily. This is the far field scatter power. Okay, this S is the far field scatter power. This is the absorption power by the lossy material. Okay. So dW dt also same equation. Okay, also same equation. Also same equation. Just like this. Imaginary part Green function. Imaginary part Green function. R and the source and the field are overlap each other. Okay. So this is how to increase the radiative power or control the dissipative power of this dipole emitter. Okay, okay, has a break, 5-minute break. The radiation process does not dissipate the energy of oscillator. You can see the dipole oscillator. When they emit power, they will damp. They will damp. Okay. When they are damped, they call it the radiation damping. They have some reaction force. They give some force. Okay. Just you know, when you emit the EM field, they have to give a force over this dipole source. This is a harmonic oscillator. So this MA is harmonic oscillator. This is force. Okay. How to calculate the force? It's easy to calculate because the energy dissipation must equal to work exert on the oscillating charge by the radiation force. Okay. I mean, when they emit power, they have a force given this dipole. The F dot V, the R dot is V. FV is power. This power, it should be equal to this total radiative power. Okay, a total radiative power. Okay, this total radiative power just E. So how to get this F? F R equal to F V. Okay, equal to E T plus H T something. ds. Okay. Equal time domain. Okay. Something like this. Just balance. Okay. This is the power. It's also a power. So this. Finally, I do some simplification. Okay. This is for they can divide by yourself. Okay, not difficult. So F finally you can get this some expression. So there's a very interesting thing that there are two interesting things. First, the energy dissipation rate, I mean this radiative power. The radiative power equal to R double dot. What's the meaning of that? Acceleration, right? The QR is Q equal to R is a dipole momentum. The R, the second order or R is first order is velocity, second order is acceleration. So what's the physical origin? It means when the electron accelerates, they will emit electromagnetic wave. Right? If electron is accelerate, if no acceleration, they do not radiate like DC current, right? Current also move, but there is no acceleration. Okay, they have current, but they don't radiate. This is acceleration. Okay, it's acceleration. Why is acceleration squared? Because it's power, like E squared, right? It's E squared or Imson, right? ds something, right? For far field, you can use the thing, right? So it's R squared here. Okay. So FV is a power by this force, okay? By the radiation force. This is by the radiation power. They are balanced. I do the integration by part. This R, I put this R is R dot in here, so it's I3 dot. So the radiation force is proportional to the R3 dot, just similar to acceleration, then do this d over dt. Okay. Acceleration and do d over dt, R3 dot. Okay. So R dot is V, R double dot is acceleration, R3 dot is acceleration of d over dt. So this is called Arnhem-Lorentz formula. It's very famous in physics, so this is force. Okay. So, okay. So I do some approximation. Okay. If I see, I said it's damping, but its force is small. The force is small. I do some approximation, and this R3 dot still equal to omega 0 R dot. Okay. I said the decay is small. I ignore this decay. It's a harmonic oscillator. So R3 dot is just omega square R dot. Okay. I mean, omega square is just R double dot from this equation. So finally, I get this was Lorentz form. Okay. This is gamma 0. What's the gamma 0? The gamma 0 is just a decay rate. Just a decay rate for this harmonic oscillator. Okay. You can see we know the force can be proportional to R3 dot. Okay. R3 dot. Okay. We also know R3 dot equal to omega square R dot. So put them together, I get this gamma 0 is something like this. Okay. Gamma 0 is something like this. Okay. This is the bandwidth. This is the bandwidth. This is bandwidth, just decay rate. The electron dipole, when they radiate the electromagnetic wave, they will decay. Okay, they will decay. It has a bandwidth. They call it gamma 0. But I think this page is a very interesting thinking. This thinking is a motivation for quantum theory. Okay, for quantum theory. Why the classical theory cannot explain this? Okay, this is very interesting. Just think. Okay, if an emitter similar to atom, molecule, or quantum dot, okay, because it's very small, it behaves like a dipole source. If this dipole source spontaneously emit photon, I mean in a dark environment, it's a very dark environment, you'll see some molecule can emit light, right? I don't know how to say in English. 那个坟地 I don't know how to say in English. In tomb, maybe you see some color, right? You see some light, right? It's spontaneous emission. Okay, spontaneous emission. A very dark environment. Okay, it's spontaneous emission. Okay, but according to classical theory, if the dipole spontaneously emit photon, they will decay. Because it has force, they will decay, right? It has broadband, they will decay. It has a finite bandwidth. Okay, the bandwidth is just equal to its decay rate. Just equal to its decay rate, gamma 0. Okay, so the undriven oscillator will come to rest. They will decay. If no one gives his force, they will rest. Right? You are saying out the atom emits photon, they decay. They just come to rest. But in fact, they do not come to rest. This is the fact. Who gave his force? Right? Gave his driven. Okay. This is the thinking. Okay. Then from quantum electrodynamic view. Okay. The quantum electrodynamic is 50 years ago. Just invented 50 years ago. The electrodynamic fields fluctuate in a vacuum. Okay. What mean of fluctuate? They means in vacuum. I mean in a dark environment. You just see very dark, cannot see any light. No laser, no this light, no laser. Even in a very dark environment. In classical theory, we assume that E field is equal to 0. This is classical theory. So they will come to rest. But quantum theory said no. The mean value or expectation value of E field is equal to 0. But there are variation. They have some standard deviation, like a noise. Okay, they still fluctuate. Okay, they still fluctuate. This is quantum theory. The fluctuation vacuum field compensates the dissipation of oscillator. Okay, right? They make this does not move. They just oscillate. Okay. So in short, to preserve equilibrium, it's very important. Equilibrium between the oscillator and the vacuum must give the fluctuation because it takes energy from the oscillator. When the atom oscillate, they emit the EM field, go to the vacuum, right? But also, the EM field also return back to react with dipole. They are balanced, similar to black body. Remember black body? Black body also said, oh, they has some absorber. they absorb the EM wave from outside, right? Produce some final temperature, then they emit EM field. They are balanced at thermal equilibrium. Similar to this, or the oscillatory, they emit EM field. EM field also return back to react on this dipole to make this continue. Okay, this EM field is the intensity is very, very small because it's in vacuum, in dark, very small, but still has variation, still has some fluctuation. They call this is called fluctuation or vacuum fluctuation field. Okay. This is okay. So consequently, we can add a driven term. Okay, according to this fluctuation field. That means in this field, you can see this is Kx. This is oscillatory. This is decay. No driven. I can add some driven to balance them. Okay, add some driven. This driven term is related to the fluctuation field. Okay, this driven term it has a name called Lagrange random source. Called Lagrange random source. Okay, everyone know the Lagrange. Okay, Lang Zhiwan, very famous physicist. Lagrange random source. Okay, which is also physical origin of 3. Brownian motion, Johnson noise, black body radiation. Many phenomena just do this. Okay. At thermal equilibrium, the physical process obeys what's called the fluctuation dissipation theorem. They call it fluctuation dissipation theorem. I will explain this intuitively. Okay. Why is the process dissipating energy? There's a reverse process for compensate the energy. Okay. Okay. I give first case called Brownian motion. Brownian motion. Some molecule, you put some in water, you can see they move, right? They move very fast. Why they cannot stop? When they move, they have friction force, right? They have drag. If friction force, the speed will become lower, then stop. Why they still move along? When they have to friction, they have produced heat, right? Produce heat. The heat, kBT, also increase the kinetic energy. Okay, so they have a balance. They have detailed balance. Okay, so one process dissipate energy. I mean they have friction force. They dissipate energy. This dissipated energy converts to the thermal energy. The thermal energy also increases kinetic energy. Okay, this is thermal equilibrium. Okay, it's called Brownian motion. Another is Johnson noise. When you measure any device, you see the noise. You see the noise. Because the resistance absorbs the electromagnetic wave. They absorb, they also emit. They balance each other. They absorb, they emit, similar to black body. Okay, you see this fluctuation current. Okay. So you know the famous equation called kBT equal to B. kBT equal to B. B is bandwidth. Remember this equation? kBT will be what's the kBT? Average energy per mole. kBT is average energy per mole, right? B is the bandwidth. Okay. Because they should do all the bandwidth. So this is also due to this effect. We call it fluctuation dissipation theorem. This theorem, this is someone first, or maybe the pioneer researcher, invent this theorem. You know who? You know this very famous guy in signal processing. It's a very famous theorem called Shannon and Nyquist sampling theorem. It's a Nyquist, right? Nyquist famous Johnson noise. Okay, they give the kBT over B is the equation, and then they explain this with the fluctuation dissipation theorem. It's by the Nyquist. So the great physicists they do a different field. Okay, they understand this by the thermal equilibrium. Okay, so this is a very important. You can understand by yourself. Okay, it's a fully reversible, it's a fully detailed balanced procedure. Okay. So there's a process to dissipate energy. There's a reverse process to compensate this energy, to make this just balance each other. So this is a very interesting topic. This is a classical picture. I finished this picture. Then we talk about the Hamiltonian. Okay. This is semi-classical. We talk about the semi-classical picture. This vacuum fluctuation recently very popular. This another thing called I'm not sure you hear about called Casimir force. You hear about this force. Everyone know force typically I put here they have force, right? What's meaning of Casimir force at a nanoscale, very small nanoscale. When the two objects very close to each other, they have a force. In the dark environment, no incident wave, they have a force. Why? Because fluctuation of electromagnetic field. E field is not equal to 0, like random noise. Okay, so this field gives this force. So when you design your called MEMS device, you should be very careful when they're very close. They will touch. They will touch each other. They will break. Okay, this is by this vacuum fluctuation with electromagnetic fields. Okay, like a black body, like many things. Okay, like a noise called Johnson noise, just from this fluctuation distribution theory. Then we talk about this Hamiltonian Hamiltonian approach. Hamiltonian is I worked in this Hamiltonian system when I was a PhD student. I benefited I want to learn this part. So I give a very simple example. Consider a sphere, the classical physics. When falling down to the ground, okay, I assume that it has zero potential. It has zero potential reference here. How about the total energy of the system? H, the total energy of the system, is a kinetic energy P dot P equal to 2m plus kinetic and plus the potential energy mgr. This is the total energy. Okay, P equal to mv. Okay, mv. So here it's just we see that it's F102 mv squared. Okay, so this is energy conservation, right? When the sphere falling down, the kinetic energy will increase, right? The potential will decrease. They have minus. The kinetic energy will increase, the potential will decrease. Add them together is constant. Okay, add them together is constant. So it's the total energy of the system. The total energy of the system. It's just kinetic energy minus potential. It's kinetic energy and potential energy. Add them together. The minus is due to because kinetic energy increase and the potential energy will decrease. So it's called energy conservation. You learn this in high school physics. But the time evolution of a system is unique determined called a Hamiltonian equation. It's very interesting. If you notice, if I can write this Hamiltonian of this system, I know the motion equation. Okay. So first, we see this equation. This equation is very symmetric. dp over dt equal to minus partial h partial r. And the dr over dt is positive partial h partial p. This is called a Hamiltonian equation. You can see this is negative, it's positive, this is p, this is r, and I change the position, this is r, this is p. This is called a Hamiltonian equation. So from this equation, we can see what happened. Okay, partial p or partial t. Everyone know partial t or partial t equal to F is a force, right? Minus partial h to dp over dt. Sorry, not partial. This is no pd equal dp over dt. Okay, so dp over dt equal to F. And minus partial h or partial r. What's minus partial h or partial r? Mg, right? It's mg. You can see. Because I see the p and r are independent. P and r are independent variable, and the partial h or partial r is just minus mg. They have minus here is mg. You can see here. So we get what? We get this Newton's law. This Newton's law. And from this equation, get this Newton's law. Another equation is same. dr over dt equals to partial h over partial p. Okay, partial h over partial p just p squared is 2p p over m. Right. Just p over m equal to what? Weight. Okay. So this is just velocity equal to the change of the displacement. Okay. So you can see this Gaussian equation can be written in so elegant form. They call it Hamiltonian equation. Hamiltonian equation. This form can use for any conservation, any system, if the system has any conservation property. Okay. If a system has, if any system, if a system energy is conserved, you can use this, get this Gaussian equation. So this is very important. Okay. Then we talk about the Maxwell equation. The Hamiltonian equation for Maxwell. For Maxwell equation. Okay. I right now for Maxwell equation, the total energy, total stored energy, 102 equals E squared plus 102 mu HRT. I use time domain. dV. Yes. This is total energy, right? It's total. It's free space. Sorry, it's free space. It's very simple. No charge, no source, sourceless region, free space. Yeah, this is stored electrical energy. Is stored magnetic energy. It's stored magnetic energy. So for Maxwell equation, people just do a little bit a channel variable. Okay, here I can change this to y. We call it y. Y is similar to the electrical flux. We change to y over epsilon 0 to epsilon. Okay, this is a change to y. So y definition of y is minus epsilon e. The reason I'll show this later why I use minus epsilon.
Not responsive moments.
No reason. Oh. So why try to reconnect? Oh, see my. Oh, why my this connect? Oh, I know because Hong Kong only has a limited time to use Wi-Fi. I don't know why, the condition is where I use TeamView because cannot support in my service. I use this to show.他说可以，
应该是可以啊。
啊？
你看后面是你的桌面。
啊？
后面是你的电脑。
哦，已经可以了。OK。好，把这关。Okay, so I only use this method to shoot. I don't know why the equipment is so bad. Then I change use the vector potential. Okay. This delta cross A is a vector potential. It's B field. Here, delta cross A just equal to B field. Just use some channel variable. So, how about the Gaussian equation? Just partial y, partial t, variational principle, partial h, partial a. And partial a, partial t equal to positive partial h partial y. They're quite similar. You can see quite similar. If I see the y as a p, I see the a as r, everything are same. Because everything are same. Similar to this. I just see that. The y is similar to the electric flux. The a is a vector potential. Everything are same. Then I derive the equation for you to check whether it's right or not. Okay, the second equation is very simple. Partial a or partial t equals to partial is a variational principle, delta h and delta y. Okay, delta h or delta y is very simple, just y over epsilon 0. Okay, y has minus. This is the reason. It's minus e. Right, you learn this, but it's so easy. You learn this, you know E equal to minus partial A, partial T, and minus delta phi. Right? It's a vector potential. You learn the vector potential. Because I said, because the delta cross E equals to partial B over partial T. I show this. And the B equal to partial T delta cross A. Right? So I know the E field equal to partial A and minus delta phi. Here, gradient phi equal to 0. I use Coulomb gauge. Okay. In free space, no charge. So phi equals to 0. Okay. Because phi satisfies boundary condition at infinite. But r goes to infinity, phi equals to 0, and phi is continuous. So phi equals to 0. Okay. So this is the first equation, E equals to minus A, or the second equation equals to minus A minus T. The first equation is also right. Partial Y, partial T, okay, equal to minus partial H over partial A. Okay. This is delta A dot delta A over 2 epsilon. Okay. Use integration by part. Okay. I can do this delta cross A, gradient A, 2 mu 0, then plus A delta cross A, 2 mu 0. This is delta A, dV. So pull them together, just delta cross A, or mu 0. So this is delta cross A, mu 0, minus. So here, just the Maxwell equation. Okay, just Maxwell equation. You can check. Just Maxwell equation. I go to the next page. You can verify. Because of y equal to minus d. Okay, it's minus d. Minus d equals to minus delta cross h, because no j is free space. Okay, so delta cross h just delta cross b or mu, b just delta cross a. Delta cross a or mu 0 is just the variational principle h or delta a. Okay. So it's very nice. So if you notice energy, as always, energy change to this is Gauss equation. This Gauss equation, Hamilton. It's Hamilton. Then I go, okay. I go this Schrodinger part. Okay, the Schrodinger equation. This equation is just gas. Schrodinger gas is equation. Right. In sometimes I remember sometimes people want to explain some quantum phenomenon and no governing equation. They guess, just guess, cannot verify. They can do some experiment and say, oh, this equation is right. But the first Schrodinger gas is equation. Okay. This is interesting, right? Schrodinger. But this equation is something like this. It's I h bar, partial t phi. Phi is wave function. H is operator. Okay. So say that the H is Hamiltonian operator. Okay, it's operator. It's also kinetic energy plus potential energy. Okay, kinetic energy plus potential energy. But P in here is not a classical momentum, but it's some operator. P equal to minus I h bar gradient. Okay, we call it momentum operator. Okay. This is the Schrodinger equation. Okay. What's the physical meaning of phi? Why people study the Schrodinger equation? So phi is just a probability. Just a probability of the electron at some position. Okay, phi square is a probability in quantum mechanics describing the quantum state of particle at a position r or t. Okay. So I just draw this equation, see what happened, see why Schrodinger can think about this equation. So this equation is not so in frequent domain, if I draw this in time domain, first I draw it time domain. I do the frequent domain. Here is E. The H is just minus something. Equal to phi. RT. Okay, something like this. If you do some change, this delta square, this Laplacian operator. So this is similar to what? Similar to the wave equation. This is the wave equation. This is the wave equation in Maxwell equation. Similar to Maxwell. This is the wave equation, scalar wave equation. So this equation is similar to scalar wave equation in frequent domain. So here, I just do channel arrival. So why Schrodinger can think about this? It's a h bar square 2m delta square and plus v, okay, then minus e equal to phi. I just delta square plus e minus v over h bar 2m phi equal to 0. If I say this with k square, it just said, okay, just said, okay. So they said electron similar to photon like a wave, similar to photon like a wave. They also can be interference. This is very important. This is very important. Electron similar to photon like a wave also can be interference. The phi is a complex. Phi is a complex called a probability amplitude. It's complex. They have real part, imaginary part, so they can interference. I ran through this experiment. If for this screen, I give, there has two slots. There has EM wave to here. The system interference pattern, right? The system interference pattern. For electron is the same. If you use some electron, right? There's some film, some filament. You heat up, they can show the electron. The electron randomly. They have a probability go here. They have a probability go here. You don't know, right? But many times, you watch many times, you see interference pattern at the screen. Okay, they have some interference in the screen also, similar to photon. Okay, because the electron also satisfies the similar to wave equations. Okay, the phi is a complex number. This is very important, so they can interfere with each other. Okay, so the phi square is a real number. It's a real number. This is a probability. This is a probability to find the electron. Okay, let's give an example. If something like this is nuclear, it's 3D. I cannot draw this. Maybe I draw this 2D picture. Okay. It's X, it's Y. Okay. Maybe it's higher, this is smaller. Okay. If this is higher, it means it has a larger probability to find the electron here. This is smaller, it means it has a very little probability to find the electron around here. Okay, so phi square just give the probability, and phi square RT minus infinity goes to infinity dr equal to 1. It's a probability. It's a probability. Okay. So they must get, okay, phi in itself is complex. It's complex because it will interference. They can be interference. Okay. The phi, the amplitude square is a real number. It's a probability. Okay. Like you know, you see some hydrogen atom. You see some two hydrogen atom. Two hydrogen atom. So the electron here is very thin. So phi here is a higher value. And here is a low value and high small value. This, okay. Phi square. 1. Because it has a chemical bond, so electron has a larger probability go around here. Okay, but has a small b probability around here. So phi, the amplitude square, is give the probability to find the electron at some spatial point. Okay, this is the Schrodinger equation. From the Schrodinger equation, right, this is very important. This part, because if everyone knows de Broglie, right? His PhD thesis only has 3 pages. They get a PhD, 3 pages. They found this P equal to h bar k and E equal to similar to that, E equal to h bar omega. PhD thesis is only 3 pages. Okay, so I can derive. I can use the plane wave. This is plane wave, right? A is amplitude, omega t kr is plane wave in photon. Okay, I use this plane wave to substitute to this Schrodinger equation. You can verify this. Okay, you can verify this. The one is the Schrodinger wave, like a waves. Okay. So if there has a plane wave, the plane wave is eigen solution. It's eigen state. It's kr minus omega t. Okay. This is a wave equation. I substitute to this I h bar partial t phi h, something like this, equal to h bar RT. Here is just P is kinetic energy plus potential energy. But the P here is operator. So I just show this is h bar square 2m Laplacian operator phi plus v phi. This is Schrodinger equation. So I see the left hand side. So I h bar partial t, okay, equal to e I k r minus omega t here. So why they put h bar in here? You can see here. They just put this I h bar e I k r minus omega t, then minus I omega, just h bar omega e I k r omega t, just e I k r omega t. So do this. This is left side. The right hand side, this part phi, okay, this is just e h bar 2m Laplacian operator e I k r minus omega t. We just do this twice, just I k, right? Because this is r, okay, 12. Why they can guess? This is the reason why they can guess this equation. H bar squared 2m e I k r minus omega t is same. So this here is just h bar squared k squared 2m, just h bar k squared 2m, just p squared 2m. So I finish all. So this is the reason why they get the form like this. They know, first they know that, they assume that P is a momentum, right? Because they said electron like a photon, or electron like a photon. Everyone knows the photon momentum is similar to K, because we said the phase matching is similar to momentum matching. It has a universal constant h bar in here. So if I assume P equals to h bar K, this should be like form like this. This is constant. Because the delta this Laplacian operator, when two Laplacian operator, they have a K square, right? That's a minus K square in here. Okay, so this is can be get this. This is kinetic energy. This is kinetic energy. Okay, so this is constant. Why they have minus? Why they have h square 2m constant? Okay, if we want to get the p square 2m, they also have I h bar constant here because they have omega. H bar omega equal to e. Okay, so they know this. So they have so Schrodinger just according to the de Broglie and Einstein. Einstein found E equal to h bar omega. They found when they do the experiment, I remember when they do the experiment, they see the spectral line of atom. They find all the spectral lines are not continuous. They are discrete. And the minimum discrete distance is h bar omega. They found that. They do the experiment, found initially classical theory said, oh, this spectral line should be continuous, but they found it's discretized, like quantized. Okay, so Einstein found that E equal to h bar omega. Oh, they found that. It's by the Einstein's quantum hypothesis. Einstein's. Okay. Now de Broglie found this P equal to h bar K. Okay, because P is a momentum, K is a phase vector. They also can connect to h bar. This is by the de Broglie. Okay, the Schrodinger, according to these two findings, just guess this equation. They know the equation should have a plane wave form, right? It should have E I omega t minus kr. They should know the eigensolution should this form. Then we guess it's constant, right? Because this constant recover to E. We have h bar, right? This constant recover to this kinetic energy. So everything I guess. Right? They guess these equations. This is very big progress. At that time when this equation appears, all the physical scientists become very excited. Okay, and they use the equation to verify the experimental results. All I totally agree with. Okay, so this is Schrodinger equation. This Schrodinger equation. So I go to a last page. See what interesting thing happened. Okay. If we know the Schrodinger equation, this is Schrodinger equation, right? This H is operator, is a Hamiltonian operator. Okay, how to get this expectation value or mean value, right? This is what probability, right? Because phi amplitude of phi square is the probability. So H multiplies to the integral is expectation value. Right. You know the phi square, you can know the expectation value. Okay. Then I have the phi square, I can do the phi conjugate equal to phi. I do the inner product. So any operator, H is operator, because P, well, V is just classical, VRT is potential. But the P here is operator, becomes some Laplacian operator, right? So this is the operator. The operator should have the expectation value. How to get the expectation value? Just multiply this probability distribution, phi square, phi amplitude square, and do the integral. Okay. So this is just statistics. Then I split phi amplitude square equal to phi conjugate phi. Okay. Then I write this inner product form. This form is also very famous. This notation is called bra. Okay, I read the reason. It's called bra. This is called cat. The bracket notation. Okay, and this is mean a phi conjugate H and a phi. Okay, this is a real value because H is a Hermitian. This is a real value. Okay, I use HQ. H is operator, but HQ now is a function. It has a classical. I also can get this Schrodinger equation. You can see everything are similar. If I say this is a P, it's a Q, it's similar. They have some constant in here because it's a quantum. It has constant here. I also can get the Schrodinger equation. Do the same thing. You can see. All the things are same. I go to the first page. Initial, so initial, I just use a very simple case. It's right. I use this governing equation. I get Newton's law. Okay. Partial P of partial T equals to partial H partial R partial T equals to partial H partial P. Right. Then I do the Maxwell equation. Use electric flux and vector potential. Also get this governing equation from Maxwell equation. Then for Schrodinger equation, I also can get a Schrodinger equation. But here, the Hamiltonian is to use the Hamiltonian operator and the wave function, and I can get the classical form. Okay. So this is all the logic. Okay. Exponential value. Okay. All the quantum system. Okay. So I think I should stop here. So any question about this part, about this Schrodinger equation or Hamiltonian system? A little bit difficult.